Okay, we're going to go ahead and switch gears here and talk about experiments. But before we do an experiment, as it were, we're going to talk about a specific experiment. I want to make sure you got a little bit of vocab here. All right. The first term that we're going to talk about is replication, or replicating an experiment. Replicating an experiment means that you do the experiment on more than one subject. The subject is somebody who participates in the experiment, or you have the ability to repeat the experiment over and over and over. I'm going to talk a little bit about a way to teach calculus. We'll set up an experiment for teaching calculus here in a minute. So if I want to replicate my experiment, that means that if I'm going to use a different way to teach calculus, I'm going to use that on more than one person for obvious reasons. That single person may perform really well with the new method of teaching, or they may perform poorly. So we don't just want to take one data point, is basically what that says. Also, what would be nice is if I could duplicate that experiment over the course of, say, a number of semesters. All right? So that's replication. Let's talk about blinding. I'm sure you've heard this term before, but let's have a little chit-chat here for just a sec. All right, blinding is real simple. You basically blind people that are participating. You don't like throw acid in their eyes. That'd be against the law and painful. But you make it so that they don't know whether or not they're receiving the treatment or not. Okay, so in the case of the calculus experiment, if I've got students that I'm teaching calculus in a new way, in an innovative way, I don't want them to know that they're receiving a treatment, because you can get something called a treatment effect or a placebo effect if people think that they're getting a treatment and they're actually not getting it. Single blind means the subjects don't know if they're receiving the treatment or not. So you're sitting in my calculus class and you have no idea whether you're getting a new and innovative way or not. Double blinding means that both the subject and the person running the experiment, the people in interaction with the subjects, don't know who's getting a treatment. So if you're talking about a medical, like a pill experiment, the people giving the pills to the people to take don't know whether or not they're getting a placebo or they're getting the actual drug that they're trying to test. Now, in the calculus case, it's impossible to double blind. I'm the one teaching the class. I know whether I'm teaching an innovative way of teaching calculus or if I'm teaching just the regular old. Okay? Controlling. Let's talk a little bit about controlling, because really controlling your experiment is the biggest challenge. It's the biggest hurdle that we have to overcome when we do statistics, when we do statistical research with experiments. At its absolute simplest, it's really ensuring that there is a control group. That's the first place that you start. There has to be a group that isn't receiving the treatment so that we have something to compare the treatment group with. That's the reason that we do that, is we are trying to control the effects of the treatment. If we see a difference in the two groups, we can say, okay, this probably happened as a result of the treatment, like in the calculus case, because I changed the way in which I teach calculus. That's the reason that I saw a change in the outcomes. What happens when we don't control properly is we get what are called confounding variables, and that's where the experimenter mistakes the cause of the difference between the two groups. Let me give you an example. Let's say that I have a first period calculus class and I have a fourth period calculus class. Here at the Davidson Academy, fourth period comes immediately after lunch. And I use the innovative way to teach calculus during fourth period, and I use the rank and file way to teach calculus during the first period. And then at the end of the semester, I compare the grades, and voila, behold, I have better performances on assessments in my fourth period class. Now, hopefully, your spidey sense is tingling here a little bit. There should be bells going off. It's like, wait a sec, Ripley, first period, kids are asleep. Maybe they're not paying attention. Fourth period's right after lunch. They got some exercise. They're a little more focused. They can pay attention. Exactly. I have confounded, or I have mistaken the cause of the difference in scores. I've confounded it with the time of day that the kids took versus the actual treatment effect, what the treatment did to the students. All right? That's confounding, and confounding is a major problem, and that's the reason why we seek to control a lot of those things. And I'll give you some techniques for doing that. Okay? All right, so real quick, making a bomb-proof experiment or observational study. Remember, an observational study is we just observe stuff that's already happened, versus an experiment where you actually have to come up with a design and have all sorts of fun with it. okay, which we'll get into here in just a sec. An observational study is make sure that you clearly define your population. You always want to make sure that you do that, and randomize your data as best that you can. Sometimes it's really, really difficult to truly randomize data that comes in. And then, of course, do good math. Sounds a little simple, but it's true. Don't screw up on your math. And especially in the age of computers, there's going to be a lot of software packages out there that'll spit out values, and we've all heard that garbage in, garbage out. If you don't know what you're doing, then you're not going to know what you're looking at when the computer gives you a number, and you may misinterpret it. Okay? For an experiment, it's a lot more complicated. You want to randomize members of both the control and treatment groups. You want to be able to replicate your experiment. All right? Think of replication. If you've done the replication properly, basically you could write up a set of instructions and pass it off to somebody like-minded, and they could do the exact same experiment. They may not get the same results, but they'll be able to do the exact same experiment. So that's a way to sort of simply replicate your experiment. You can describe it really easily how to replicate. Okay, blind your experiment as much as is practical. Sometimes it's not practical in the example that I gave you earlier. All right, and then of course watch out for confounding. When I say watch out for confounding, what I mean is always be real critical as you're designing your experiment, saying, okay, what else could cause this other than the treatment that I'm trying to prove caused a change? All right, is there anything else that could cause a change? Okay, all right, so you got a little bit of vocab. I'm going to go ahead and pop over to my tablet here, and we'll design an experiment. We'll talk a little bit for a few minutes about how to design that calculus experiment that I was talking about earlier, and then that'll be the end of the chapter. Again, I apologize for too much use of the PowerPoint, but we're going to get out of that here in a little bit. We'll have to endure a little bit more, but not so bad. All right, hope you enjoyed. I'll see you on the tablet. Hey everybody, we're back at the tablet. Let's do a quick little experimental design here. All right, let's say that there are a grand total of, we've got a population of kids, and there's 1,000 of these kids taking calculus. All right, so I got 1,000 calculus kids. And what I want to do is I want to see the effect of an innovative way of teaching calculus. So let's say that I'm going to flip my classroom like I'm flipping with you guys, where I give the lecture material online, and then in class we just do mathematics, and we practice, and we get into some of the deeper level stuff. Okay, now there's several ways that I can select my sample. I don't want to deal with all 1,000 kids, especially on a university campus. That's sort of a logistical nightmare because you got kids coming and going and doing all kinds of things. Okay, so let's say, just to keep it simple, let's say that I want to have 50 kids. I want 50 kids in my experimental, and then I want 50 kids in my control. Okay. All right, now one way to do this is called a completely randomized, let's go, completely randomized design, or experimental design. Okay, now the way that this works is really simple. It's actually the simplest of the things to do. However, unfortunately, it's not feasible. What we're going to do is we're going to take all 1,000 kids of these guys, we're going to assign them a number, and then, so I got 1,000 up here, and then I'm going to randomly select the kids to go 50 in here and 50 in here. This is, again, my experimental, and this is my control. All right, so I would number the kids 1 through 1,000. I'd pull out my fancy schmancy random number generator, and I start pushing numbers until I got 50 in the experimental and 50 in the control. You can probably see the problem with this. The problem with this is that if I do it in this way, is that I've got 1,000 kids that are spread across a number of classes that they may or may not have already registered for. So let's say of the 50 kids in here, that may be spread across a whole bunch of different sections or different classes. How are you going to teach to just those few kids that may be in one class and leave the other ones behind? So in this case, a completely randomized design doesn't work. Sometimes they do, but not necessarily, okay? So in this case, that's not going to work. Again, I can't teach to 3 of the kids in a 40-person class with my new and innovative way because they happen to have been selected for the experimental group, okay? So there's a way around that. What we do is we're going to do a randomized block design. Whoops, block design. All right, now here's what we're going to do. Let's say that I've got 50 kids and we're teaching big classes, so bear with me. Oops. We're going to have 10 classes every semester. All right? Did I say 50 kids? I meant 1,000, et cetera, et cetera, et cetera. All right? So what we're doing is we're blocking the kids by the classes. This is class 1, this is class 2, et cetera, class 3, and then out here is class 10. And we're blocking them by their classes. And then what we do is we're going to randomly select which of these classes we're going to do the experiments on until we get up to 50 kids. And then we'll randomly select which of the kids out of those classes get included in the data. So let's say, just for giggles, that class 1 has, let's see, what do we got? Let's keep it simple. Class 1 has 100. Whoops, not 1,000. Sorry, guys. Has 100, 100 again, just to keep it simple, et cetera, all the way out to 100 each. I'm going to randomly select 2 of the classes, one of which is going to be, so let's say this guy gets selected, and let's say this guy gets selected. Okay? Then I'm going to randomly select which one's going to be the control and which one's going to be the experiment. So you take a random number from 1 to 10, pop it out, that becomes your experimental. The other one becomes your control. Okay? Remember, experimental gets the treatment. They'll get the new way of teaching. The control gets just the regular old, I'm going to lecture to you, you're going to go home and do your homework, et cetera, et cetera. All right? Now remember, though, there's 100 in each one of these classes. So then what we do is, again, I only want 50 in each one of the, in each group when I'm doing this, in each of my samples. I would randomly select 50 of the kids to collect data from. Now the other 50 kids still take the class, they still get the information, but I don't use their data. All right? They have no idea that they're receiving a new and different treatment, but they're part of an experiment that they don't know about. Okay, now you're going to hear me say your spidey sense is probably tingling here. Sometimes you can get something that I affectionately call cross-pollination in an experiment, and this isn't actually in your book. But the problem is let's say that the kids in the experimental group really like the new way of doing things, and all of a sudden they start yapping. They start yapping about what's going on. Well, some of these control group kids are going to find out about it. Now, will that have an effect on your results? Will that have an effect on your data? Maybe. Maybe it doesn't. But that's something that definitely has to be addressed, because then we might see changes that we don't necessarily, that aren't necessarily accounted for by the treatment alone. And remember, we call that confounding. Confounding is muy malo.